Well, good evening and welcome to lecture number 10 for MT225. Uh, Tonight we're going to be continuing on with equilibrium problems. This is really the last new material before our first exam a week from Wednesday night. So this will be the last new stuff. There will be a homework assignment issued on this on Wednesday, but as I mentioned last time, that'll be a bonus assignment. So it's if you do it, turn it in on time. Any grade you get on that that is better than one of your other homework assignment grades, it will be able to substitute for it. So, but it's not officially due. I don't want to overstress how many things are due on that particular date. So let's carry on here. Homework 3 was sent back over the weekend. So if you submitted homework 3, you should have gotten a response on that. For the most part, performance was pretty good. A few little bits and pieces here and there, but no major trouble spots. Um, Homework 4 is due on Wednesday, and I'll open up the floor for questions on that here in a moment. Quiz 3, if you haven't turned that in already, and several people have turned that in already today, but that is due before midnight tonight. So make sure you get that turned in. Quiz 3 based on homework 3, so concurrent force problems. And then the big announcement, big official statement here in the notes for that. Exam 1, our first exam, Wednesday, March 17th. It'll be at 5 p.m. in the new hangar. I haven't decided exactly what room yet. We'll probably go for the room that's being used by power plant right now. That seems to be the most set up, so we'll probably use that, but we'll figure it out when we get there. And you can have a 4-inch by 6-inch reference card. You can use both sides of it. Anything you want on that is fair game. So example problems, equations, whatever you might feel necessary to put on there. Don't bother putting down specific unit conversions. If you need to convert units, I'll tell you what the relationships are, so you wouldn't have to have a whole table of references on your note card. Save the note card for things that will help you out during the exam. So maybe an example of how to convert units might not be a bad thing to have on there, but I wouldn't put on there 1 gallon equals 231 cubic inches or anything like that, because you just couldn't know what I could possibly pull up. But that 4-inch by 6-inch reference card, bear in mind that you will have access to that during your second exam as well. The way I've set this up is if you use, you have an option on the second exam to use 2 reference cards, on the third exam 3 reference cards, and the fourth exam you can use 4, the final. You can use 4 of them. You can choose to use cards you have used previously. So if you make up a pretty good card for this one, it might be useful to you on exam 2 or exam 3 or the final as well. There's no requirement you do that. You can make up 2 or 3 or 4 new cards, or make up new cards each time, but that's an option to keep in mind. Anyone have any homework questions? Anything on homework 4 that's giving you some difficulty? All right, well, we'll take a look at, I'm sure we'll have at least one problem on that on Wednesday night. There's one of them, the last problem's a little bit of a strange setup. Looks a little bit different than the other problems and the examples we've done, but it can be solved with the techniques that we've learned. So likely we'll end up working that one out Wednesday night. But if any other problems come up, be sure to raise those. So our objective tonight, the last little piece of information we need to finish out equilibrium problems, is to take a look at what we call distributed loads. A distributed load is really a more realistic representation of loads applied to structures than what we've been working with. We've been working with what we call point loads or concentrated loads, where we can definitively say this force is applied at this particular point. In reality, that never happens. If you take a sack of concrete, an 80-pound bag sack of concrete mix, and set it down on something, that 80 pounds is spread out over some area. There's no specific point that that load is applied. Unfortunately, distributed loads, which is the real nature of how loads and structures interact, is a little bit harder. Distributed loads are a little bit harder to deal with mathematically. It's a lot easier to deal with a load when you know it's at a specific point. Fortunately, we have the ability to distill a distributed load down to a point force equivalent. So this is the same story you've all seen several times over in lots of different subjects. When we have some new system or some new way of looking at something, we do our best to make it look like the old system, turn it into what we already know how to solve. And that's exactly what we're going to do. We'll see how to take distributed loads and turn them into point equivalents. And then once we know that point equivalent load, everything works exactly the same as it has for all the other problems. So we need to find that point equivalent load. And we'll do some examples with that, and we'll practice again tonight in our practicum session with some more equilibrium problems. So let's look at distributed loads. So up till now, all of our forces have been concentrated. We could, in essence, think about the forces as being applied on single atoms, a single point. Reality doesn't quite work that way. Real loads, we can't really say they apply at a specific point. And that works whether we're talking about putting loads on structures like vehicles onto a bridge, or whether we're just simply talking about gravity. You all know from weight and balance that there's not a single point on the aircraft that has the whole weight of the aircraft concentrated on it. Every little bit and piece of the aircraft weighs something. We learn in weight and balance how to distill that distributed weight down to a single point force. The point being the center of gravity, and the weight being the weight of the aircraft, the force being the weight of the aircraft. So we're going to see something similar to essentially what we do with weight and balance. In fact, the way we'd handle a generic distributed force is essentially by doing sort of a weight and balance calculation. Fortunately, we don't have to do that here. We're only going to consider two variations of distributed loads, two very simple variations on distributed loads that we can turn immediately into point forces. So you just need to know how to spot those loads and turn them into the equivalent point force. But realistic loads are not applied at a specific point. Think also of lift on a wing. Lift is distributed across the wing. Every square inch of the wing is producing lift and is producing some drag. So those aerodynamic forces are distributed, but we often talk about the center of lift or the center of pressure. Those are the imaginary points where we can think of all of those forces being concentrated. So it's the same kind of principle here. So for our purposes, we only have three different types of distributed loads, and really there are only two. The third is just a combination of those two fundamental loads. We'll have what we call uniformly distributed loads, which is basically what it sounds like. It's uniformly distributed. It's spread out evenly. And then we have what we call a linearly distributed load. Linearly distributed loads start off at almost nothing and then climb up to some peak value after some amount of distance. So it's a straight line behavior with weight or with force, and that's the way we draw them out. We draw them out so that the representations of those forces call into mind things that are uniformly distributed or linearly distributed. And we can combine the two. We can add them together. We can put them on top of each other, things like that. And we'll see a couple examples of that. So to handle a distributed load, we have to find the load's equivalent concentrated force. And that involves two pieces of information. Just like in weight and balance, you're looking at the force of gravity distributed all over the aircraft. You not only need to know the total weight, that's how much force there is, but you need to know where that force is, the center of gravity location. So essentially, in each of these distributed forces, we're going to find a center of that force. That's the location where the force is applied. And then we have to total up how much force there is. So there's always going to be two factors involved in finding out what the equivalent concentrated force is: a total amount of force and then a location where that force is. If we replace the distributed force with the equivalent point force, nothing changes about the loading of the structure. Specifically, the reaction forces at the supports will not change. There is some material difference inside the structure, but as far as the supports are concerned, it can't tell the difference between a distributed load and a concentrated load. So we turn everything into concentrated loads because it makes the analysis easier. So we have our combination of distributed forces. Those are resultants. It's what we get if we added up every little bit of force that was distributed over an area. It's the same thing we do in weight and balance. We add up all the little bits of force, or add up the weight on the nose wheel and the weight on the mains, and you get the total weight of the aircraft. So here's a depiction of a uniformly distributed load. So this is the representation we use for it. We have these series of arrows joined together kind of into a box, where you've got the height of that box staying the same. That's what makes it uniformly distributed. The symbol up here, W, is the intensity of the distributed load. It tells you how many pounds or how many kips or how many newtons of force are applied to the structure per foot, per inch, per meter. So it tells you how things are spread out. Essentially, it's a one-dimensional equivalent of pressure. You're all very familiar with pressure at this point. Pressure is a force spread out over an area. Well, we don't have area in a two-dimensional problem. We have length, we have distance. So we have a force spread out over a length. So the load intensity is the load per unit length. In a three-dimensional problem, it would be a pressure. It would be a load per unit area. And that's spread out over some, in this case, length. That's what L represents. Now, fortunately, finding out what the total force is pretty easy. The total force is essentially the area of this rectangle. If you think of the height of this rectangle as being W, the intensity of the load, and the width or the length of the rectangle being the length L, the area would be just W times L. If you think about it from a physical standpoint, W is how many pounds you have per foot. L tells you how many feet you've got. So the total amount of force is really just the total area if you think of the height as the intensity and the length as just a length. So our resultant force, that equivalent point force, has a magnitude of W times L. Whatever the intensity is times the length. That tells you how many total pounds of force or kips of force or newtons of force are applied. But that's only half the story. The total force is just part of it. We need to also have where that force is applied. And here it's not too difficult to see where it would have to be to make physical sense. This is a uniformly distributed load. Everything's even in all directions. the only point that makes sense to concentrate the load at would be at the middle. In a uniformly distributed load, the equivalent force is at the middle of the distribution. So the location of our equivalent point force is in the middle of that distributed load. So let's see how this works here. Let's try it out. Oops. So let's draw up a typical distributed load. Let's say we've got a simply supported beam, which means we've got one pinned support and one roller support. And let's put a couple of distributed forces on here. We'll have one that looks something like that. That's let's say 2 kips per foot, and we'll let that extend over a distance of 4 feet. And we'll let that distributed load start, let's say 2 feet in from the end of the beam. And then let's see, maybe we'll put 8 feet in there. And then maybe another 3 feet. And we'll have a little bit heavier heavier distributed load there of, let's say, 10 kips per foot. And we'll put that also 3 feet from the end of the beam. So that's all fully dimensioned out now. We know what the sizes are. And I guess I'll draw another arrow in there. There we go. So there we have 2 distributed forces. Now, to analyze this problem, we actually have enough information in this problem to analyze it, to figure out the support forces. But we're not going to work that out here. Our only task right now is to turn this into an equivalent point force problem, because these supports can't tell what the load looks like. It doesn't know if it's dealing with a distributed force or if it's dealing with a point force. The beam knows. The material that makes up the beam is going to be loaded differently if it's got a distributed force versus a point force. But as far as how those loads are handled by the supports, it's not going to make any difference. So we have to turn these two into their equivalent point forces, and we have to figure out where those point forces are located. So we can start by drawing the beam over again. First thing I like to do is figure out what is the magnitude of the force I'm dealing with, and just work with one distributed force at a time. So my first one here, I've got 2 kips per foot spread out over 4 feet. So essentially, I've got a rectangle here that is 2 kips per foot high, but 4 feet wide. Well, if I wanted to find the area inside here, it's just the area of a rectangle. You take the 2 numbers that you've got, the height and the width, and you multiply them together. So this equivalent point force is going to be 8 kips. Watch the units. Be careful. I'll write it out once explicitly, but I'll expect you to get the units right in the future. If I take 2 kips per foot and multiply that by 4 feet, the feet cancel out. And I'm left with 2 times 4, 8 kips. So I've got an equivalent 8 kip force here. And that 8 kip force is going to be dead in the middle of that 4-foot range. So to figure out where to put it on the end of my beam, if I'm referencing my pinned support here, I've got to go 2 feet in, and then I've got to go half of 4 feet, which would be another 2 feet. So that equivalent point force of 8 kips is going to be 4 feet in from the end of the beam. So there we've successfully translated between a distributed force, a uniformly distributed force, and its point equivalent force. We figured out the magnitude by multiplying the height to the intensity, 2 kips per foot, by the length that's distributed over. Each foot feels 2 kips. We've got 4 feet to deal with, so we've got a total of 8 kips. The location is dead in the middle of the distribution. So you look at where it starts and where it ends, dead in the middle, the balance point. Essentially, think weight and balance. Where would you put your finger to balance this shape? The only place where it's going to have no moment, where it's going to be in balance, is dead in the middle, where there's the same amount of force trying to rotate it clockwise as is trying to rotate it counterclockwise, right there in the middle. Let's try it with the 10 kip per foot force. Here we've got 10 kips per foot, and that's spread out over 3 feet. So each foot feels 10 kips, and we've got 3 feet to deal with. That's going to be 30 kips. So that's 30 kips of force. Where it's going to be located, it's going to be dead in the middle of that distribution. So right in the middle of this 3-foot range. So my equivalent 30 kip force is going to be right around there. I have to leave a little bit of schematic variation. Remember, it's not quite to scale, but the labels should all work out. So we've got 30 kips of force there. If I go from the other end of the beam, I've got 3 feet plus 1.5 feet. So this would be 4.5 feet in from the other end of the beam, and then you could figure out what the distances would have to be in the middle, or knowing that the whole beam is 20 feet long, you could figure out the geometry you'd need from there. So remember, when you find moments, they've all got to be, all the forces have to be measured from one point. So if you so you'd have to do a little bit of math here to figure out what your distances are. But as long as you've got them located, this would be the equivalent problem. So this is just like the problems we solved last week, and just like what's on your current homework assignment. So that's how we translate a uniformly distributed force into equivalent point forces. We take the new situation, we turn it into the old situation, and then solve the old situation. Anything not quite making sense there? All right, well, let's see a linearly distributed force. So that's our uniformly distributed force. The linearly distributed load looks something like this, where it starts out, depending on which way you look at it, you can either think of it as starting out heavy and then tapering off to nothing, or starting off really light and tapering up to some maximum. Well, W in this case, the intensity, refers to the maximum intensity. It refers to the height of this triangle. And if it helps you to think of it this way, you can call it a triangularly distributed force. If you want to reference the shapes, triangle and rectangle, as long as it helps you get the equivalent loads, go for it. Well, here we've got a load that tapers off down to nothing from some maximum intensity. The amount of force we've got, just like with the uniformly distributed force, is the area. Well, this is a triangle. And you may recall, if you dig deep in your memory to find the area of a triangle, we had this equation, 1/2 base times the height. Well, the base in this case is the length. The height is the maximum intensity, W. So our magnitude of our distributed force, the equivalent point force size is going to be 1/2 W times L. In fact, if you kind of page back and forth here between the two slides, you can see that, well, it's really just half of the uniformly distributed load. When we cut that in half, we get the linearly distributed load. The tricky point is figuring out where to put it. The middle is not going to work here. If this was some shape cut out of metal and you tried to balance it on your finger by putting your finger right in the middle, it's going to rotate. And if you think about it that way, your instinct would probably tell you, well, I can't support it at the middle and have it balance. I'm going to have to move my finger toward the heavier end, toward the end that's pushing down harder. The balance point of this distribution of load is going to be closer to the big end of the triangle. Exactly where? That's a little bit harder to calculate. It requires a little bit of more advanced math to kind of figure out exactly where it goes. So you'll have to trust me when I say that it is 1/3 of the length in from the large end of the triangle. There are a few geometric arguments you can make on that, but for the most part, for a linearly distributed load, the balance point, the point where that equivalent force needs to be applied, is 1/3 the length in from the big end of the triangle. So let's try that out here. Let's see how that works to translate a linearly distributed force into an equivalent point force. So let's see here. Let's get another simply supported beam going. This time we'll make the beam, let's say 12 feet long. And we'll put a linearly distributed force here from right at the beginning of the beam down to, let's do 3 feet. So there we go. So that spread out over 3 feet. And let's make this a 200 pounds per foot maximum distributed load. So that's how high this peak is. It tapers off to 0 over 3 feet. And then we'll put another one in here. That spreads out over 6 feet. And we'll have that one start out at 400 pounds per foot and taper down to 0 over 6 feet, or start at 0 and taper up to 400 pounds over 6 feet. So there's our setup. And in order to analyze the problem, we have to figure out what are the equivalent point forces. So let's redraw the beam. Deal with the 200 pound per foot force first. So we have 200 pounds per foot spread out over 3 feet. We need the area underneath there. So it's a triangle with a height of 200 and a base of 3. So we take 1/2 base times height. 3 times 200 would be 600. So 1/2 of that is 300. So this is 300 pounds. Another way to look at it is to say, well, if it was a uniformly distributed force, we'd have a rectangle here That would be 600 pounds. We can cut that in half. So it's 300 pounds. So we've got a total of 300 pounds from that first one. Then the question is where to put it. Well, if we tried to put it in the middle, it wouldn't work because we'd have more moment on one side than the other. If we think about trying to balance here, there'd be more counterclockwise than there would be clockwise. We have to put it right at the balance point, at the CG, essentially. And that's 1/3 of the way in of the length in from the big end. So we've got 3 feet. 1/3 of 3 feet is 1 foot. So we've got 300 pounds, 1 foot in from the end of the beam. So that would be our equivalent point force, 300 pounds. One foot in from the big end. Think about where that physical balance point would be. If this was some shape cut out, this triangular shape, and you tried to support it, it would have to be closer to the big end. So don't put it 1/3 of the way in from the small end. It's 1/3 from the big end. Let's try the other side here. Here we've got 400 pounds per foot spread out over 6 feet, but tapering down to 0. So again, it's a triangle. We need the area here. That's 1/2 the base times the height. So we have 6 times 4, that's 2,400. 1/2 of that would be 1,200. So we've got 1,200 pounds here. 1,200 pounds of force, 1/3 of the base in from the big end. Well, 1/3 of 6 feet is 2 feet. So that's going to be 2 feet in, 1,200 pounds. So our equivalent point force is going to be something like that, 1,200 pounds. Two feet in from the big end. And then you could go and figure out the rest of the numbers. You could go and say, well, there must be then 9 feet there. And that should be enough to find the reactions at the supports. So that's how we translate a uniformly distributed and a linearly distributed force into point equivalents. Once we have those point equivalents, it's the same old problem. Any questions there? All right, so let's see what it looks like in the generic case. Well, the generic case, we'd need a lot more in the way of mathematical sophistication to handle. Some of you may have some of that mathematical sophistication. If you have taken a class in calculus, for example, then you may have the tools to do this. In a generic distributed load, we could have essentially any shape. We could have a load that has some value there, maybe some value over here, and then does all sorts of strange things. So the intensity changes as a function of position. Well, for those of you who are familiar with calculus, this is a classic setup for the problem we call integration. Finding the area underneath a curve is the classic application of what we call integration. Fortunately, calculus is not a prerequisite for this class. So if you have no idea what I'm talking about, don't worry about it. Just we'll skip that. But if you have had calculus, this is something that you could potentially do with it. For our purposes, we don't have the mathematical tools to do that. So we'd have to have some way to find the area underneath the curve. That would just give us the magnitude of the force. Finding the position where the force belongs, that's a different calculation. It's what we call integrating the first moment of the distribution, and that's where the term moment comes from, and why moment ends up being tied up in weight and balance, things like that. So there's a lot of mathematical stuff there that's pretty classic, but beyond the scope of our class. For our purposes, we're going to deal with simple distributions, either the two we just described or some combination of them. So you can combine them together. The process is not unlike finding the center of gravity. Centers become an important idea, and that balance point, it has an official name we call the centroid of the shape. Kind of a funny name, but it's the generic name for what we call center of gravity. It's just center of whatever, center of area, center of force, center of lift. They all fall under the category of centroid. And centroids become important when we talk about beams. When we look at bending and deflection of beams, the centroid becomes an important idea. And in fact, those of you who have had sheet metal, which I think is everyone at this point, you learned about the neutral axis when you bend sheet metal. The centroid is the location of the neutral axis when anything bends, whether it's an I-beam or a piece of sheet metal or a 2x4. We'll look at that when we get into beams and beam loading later on in the semester. So let's try another one here. In fact, why don't you try this one on your own here? Take a couple minutes and don't solve the problem. You don't have to find the, well, don't go all the way to solving the problem. I'll do that as an example. Just focus on what we have done so far tonight. Turn these equivalent, these uniformly distributed forces into equivalent point forces. And I'll give you about 30 to 60 seconds or so to figure that out. All right, so there we've got the basic picture here. Not quite to scale, but we can work with it. So this has enough information to allow us to solve for the reactions. We know the geometry, we know the forces, so we've got everything we need. There are no missing pieces here. The first thing we have to do is turn these distributed forces into equivalent point forces. Well, the first force over here, and in fact, what we'll do is I'm going to jump in one step here to my free body diagram, because we are going to analyze this one. I'll work this one through as an example and a refresher from last week about how to solve non-concurrent force problems. So let's go ahead and put in our reactions at A and B as in our free body diagram. I really don't know what's going on at A here, so I'm going to assume RAX to the right and RAY up. And over here where B is, I'll assume our BY is up. Got our coordinate system, positive X and Y, and our positive moment. But now we have to put our loads in. Well, we have 2 kilonewtons, and I think this is probably the first problem we've worked out in metric too. Shouldn't throw you too much, but all the principles work the same. We have 2 kilonewtons per meter spread out over 4 meters. So each meter feels 2 kilonewtons. We have 4 meters, so we have 8 kilonewtons per meter, or kilonewtons total, not per meter. So 2 plus 2 plus 2 plus 2. 2 times 4, that's 8 kilonewtons. And where it goes is dead in the middle. It's a uniformly distributed load, so it goes right in the middle. So we'll have an 8 kilonewton force 4 feet in. Or, sorry, 2 meters in. Let's see, I'm getting messed up by metric now too. So 2 meters in, half of that 4 meters. Then we've got this 3 kilonewton per meter load distributed over 3 meters. So each meter feels 3 kilonewtons. We have 3 meters, so we have a total of 9 kilonewtons halfway. So we've got 9 kilonewtons. And that's going to be half of 3 meters. So that'll be 1.5 meters. So that distance there would be 1.5 meters. Then we'd have to figure out all the rest here. We've got another, looks like 3 meters up to B, and then this would be the other 1.5 meters. Make sure it totals up. We had 4 plus 1 plus 3, that's 8. We have 5 plus 3, that's also 8. One of the common mistakes I see people make in doing these kinds of problems is getting the geometry wrong, doing the math a little bit wrong here, and ending up with different numbers. So check and make sure your beams are still the same length after you split things up. So now that we've got the equivalent forces, the point forces, we can go through and solve this problem. So let's go ahead and do it. We've got our sum of forces in the x direction, and that's just RAX. We've got nothing else in the x direction. We have our sum of forces in the y direction. Well, there we've got a positive RAY. We've got a negative 8. We've got a positive RBY. And we've got a negative 9. Those are all our y direction forces. And then we'll have our sum of moments. And in order to do the moments, we've got to pick a pivot point. I'm going to pick point A as my pivot point. That'll knock out RAX and RAY. They won't have a moment since they push on the pivot point, but everything else will. The 8 kilonewtons will have a moment. The 9 kilonewtons will have a moment. And RBY will have a moment. And remember that all the moments have to have 2 pieces of information. You got to have an arm and a force. So let's work left to right here. We've got our 8 kilonewton force 2 meters away. So 2 times 8's 16. That would be kilonewton meters. And then we have to take care of direction. Clockwise moments are negative, counterclockwise moments are positive. So if we pin the beam to the wall at A and we push down with 8 kilonewtons with nothing else pushing, everything's going to rotate clockwise. So this is negative 16 kilonewton meters. We've got RBY, but don't make the mistake of just writing RBY in there. By far the most common error I see people make. Don't write RBY in. That's just a force. We need the moment. The moment is an arm times the force. So we have RBY, the force, but we need an arm. It's 5 meters away. So we have 5 RBY. And if we pin at A and push up at B, we'll have a counterclockwise rotation. So that's positive. And then finally, we've got our 9 kilonewton force. That 9 kilonewton force, we have to figure out the distance to that. We have 5 meters to B plus another 1.5 meters. So it's 6.5 meters. So we have 6.5 meters times 9 kilonewtons. That's going to be 58.5 kilonewton meters. Pinned at A, pushing down where the 9 kilonewtons is, that would be a clockwise rotation and negative. So there we've got our sum of forces and our sum of moments. Since this is in equilibrium, we're assuming it's in equilibrium, all these sums must add up to 0. So that immediately tells us RAX is 0, which hopefully you could predict by looking at this because there are no side loads. There's nothing pushing to the side, so there's nothing for the part of that support at A that handles side loads, nothing for that to do. We have our, so RAX is 0, so we can go off to the side here and kind of tabulate that. RAX is 0. We can't really solve our y direction equation just yet because we have too many unknowns. RAY and RBY are unknowns. So we've got to go down to our moment equation. That one we can solve. If we clean it up a little bit, we've got 5 RBY minus, if we add together the negative 16 and the negative 58.5, we get negative 74.5. And that equals 0. If we add 74 to both sides and divide by 5, I'm going to assume your algebra skills are up to par here. And we'll just jump to the solution. 74.5 divided by 5 looks like 14.9. And don't forget the units. That's kilonewtons. That was one of the repeated themes on the homework assignment on homework 3, people forgetting their units. So watch those units. So RBY, 14.9 kilonewtons. It's important to note that this came out positive. That's confirmation that our arrow is drawn the right way for RBY. It confirms our assumption, which is a pretty safe assumption in this problem, but it confirms that we have the direction right. So we can go over here in our table and write RBY is 14.9 kilonewtons up. Well, now that we know that, we can go to our y direction equation. We don't know RAY yet, but we do know RBY. RBY is 14.9 kilonewtons. And if we clean this up a little bit, we have 14.9, we have a minus 8, we have a minus 9. And if you go through and solve that, it would be RAY minus 2.1 equals 0. So RAY equals 2.1 kilonewtons. So it's again, confirmation that our arrow is drawn in the right direction. We got our assumption right. RAY is 2.1 kilonewtons up. So there we've got our final answer. Now, if you look at the problem a little bit here, if we didn't have this 9 kilonewton in there at all, you can roughly estimate that this 8 kilonewtons is kind of in the middle. So we'd expect about 4 kilonewtons on both of the supports. We're getting much more load on the support at B than we are at A because of this cantilevered section. That's what we call it when a part sticks out past the support. We call it a cantilevered section. And that cantilevered part, when this 9 kilonewtons is pushing down there, it's trying to rotate the whole thing around B. So it's doing some of the job of opposing that 8 kilonewtons that's sitting on this end of the beam. And it's doing a pretty good job of it. It reduced the load on A down to 2.1 kilonewtons. In fact, if this 8 kilonewton force wasn't big enough, if this was 6 kilonewtons or 4 kilonewtons, we might end up with A having to hold the beam down rather than pushing up to support. And that can happen. So it's always important to go back to the structure and make sure your answers make some sort of physical sense to you, and that you can reason out what those answers mean. Any questions on that example? All right. So let's try one with a, let's go back to the one we had here. We've already worked out most of it. So we'll go ahead and finish up this one as an example with the linearly distributed force. So this was our example from a little while ago. And we figured out our locations and our magnitudes of our distributed force. So now we can go ahead and figure out what our free body diagram would look like and do the analysis. So let's see how this one comes out. So one more example of a kind of simply supported beam problem. Here I'm going to leave the geometry on the top and we'll copy that in as we go. So we have our 300 pounds there. We have our 1,200 pounds there. We have a pinned support at A. So we'll call that RAX and RAY. We've got our roller over here at B, which I want to draw a force there. Call that RBY. Coordinate system. And there we go. Now, once again here, we have no side loads. So you might jump to the conclusion that RAX is 0. I would encourage you to go ahead and work it out. Let the math tell you that RAX is 0. It's good confirmation, and it will keep you prepared for the situations when there is a side load, and there very frequently is. So let's do our sums of forces. Sum of forces in the x direction, we've got RAX, but as we know, that equals 0 since there are no other side forces in the system and we're in equilibrium. So we've already got something we can put in our table. RAX is 0. If we take our sum of forces in the y direction, we've got a positive RAY and a positive RBY, those two right there. And then we've got what's pushing down. We've got a negative 300 and a negative 1200. Well, we can add those together. They're not too hard. That'd be negative 1500. And we know that sum is going to equal 0. So that'll be our y direction equation. And if you think about it for a moment, what the y direction equation is really telling you, if I rewrite the y direction equation just a little bit, if I add that 1500 to both sides, we have RAY plus RBY equals 1500. Basically, all that's saying is the forces that are pushing up have to equal the forces that are pushing down. We have a total force pushing up of RAY plus RBY. We have a total force pushing down of 1,500 pounds. And if we're going to be in equilibrium, those two had better equal each other. Because if one is bigger than the other, if we have more pushing up than it's pushing down, or if we have more pushing down than it's pushing up, we don't have equilibrium. We have dynamics. We're going to have motion. We're going to have acceleration. So the y direction equation pretty much always says that whatever's pushing up equals whatever's pushing down. And then we've got our moments, and again, we'll pick our pivot point at A, sum of moments about point A. We're going to knock out RAX and RAY, but we'll have a moment from the 300-pound force, a moment from the 1,200-pound force, and a moment from RBY. So let's put that together. And I'm going to start with RBY this time. RBY is 12 feet away. So we have 12 RBY counterclockwise, so it's positive. We have 1,200 feet, or 1,200 pounds, excuse me, 10 feet away. So that's 12,000 foot-pounds clockwise, so it's negative. And then 1 foot away, we've got 300 pounds. So that would be 300 foot-pounds, also negative since it would cause a clockwise moment. So we can clean that up a little bit. We've got 12 RBY minus 12,300 equals 0. And if you go through and solve that, RBY, possibly not that nice of a number, but we'll deal with that. 12,300 divided by 12. Yeah, not too bad. 1,025. So we have 1,025 pounds pushing up at B. So we've got our answer for RBY. RBY is 1,025 pounds up. Now we need RAY. Well, we know RBY is 1,025. RAY is whatever we have to add to that to get to 1,500. Well, that looks like 475. So RAY is 475 pounds up. And again, that looks pretty reasonable. Go back to the structure, take a look at it, and make sure it looks reasonable. Make sure that the forces on the supports are consistent with the loading. Well, here we've got much more force pushing down on the right side of the beam. We've got 4 times the force pushing down on the right side than we do on the left. So we should expect more load on our right side support, and that's exactly what we see. 1,025 pounds. So a lot of this 1,200 pounds is supported on B. A lot of this 300 pounds is supported on A, but some of it is being supported on the other end. So that's why we see lower loads there. So, but if you add them all up, that should be 1,500 pounds. Any questions on that one? Now, one more example I want to put in here, and that is looking at a combined linear and uniformly distributed load. So let's see what that would look like first off, and then we'll figure out how we can analyze it. So let's start here with another simply supported beam. What a combined uniform and linearly distributed load would look like something like this, where we have something that starts out at a particular intensity, maybe let's say 2 kips per foot, and over some distance climbs up to some other value, maybe 10 kips per foot. So that would be that's not a uniformly distributed load. It's not a linearly distributed load. Linearly distributed loads have to start out at 0 or end at 0. This doesn't start or end at 0. Uniformly distributed loads have to be uniform, and this isn't uniform. Fortunately, though, if you're used to looking at shapes and breaking them up into simpler shapes, you might look at this and say, well, this kind of looks like a rectangle and a triangle. And that's exactly how you can break it up. Let's put some geometry on this here. We'll make this 6 feet wide. But we're not going to solve this whole problem. We're just going to find the equivalent force. So just like a geometry problem, just treat the values here that are in kips per feet, treat them like they were distances. This is 10 units above the beam. This one's 2 units above the beam. So this top of the rectangle must also be 2 kips per foot there. What's left over here has got to be 8 kips per foot. So what we've really got is a uniformly distributed force of 2 kips per foot spread out over 6 feet, and a linearly distributed force that starts off at 0 and climbs up to 8 kips per foot. So let's see how that would look in our free body diagram. So in our free body diagram, we'd have our forces for our supports. The uniformly distributed force, its magnitude is the area inside this rectangle. It's 2 kips per foot high, 6 feet wide. So that's 12 kips. Where does that 12 kips go? It goes dead in the center. So dead in the center, we've got 12 kips. Then we've got this linearly distributed force. That's going to be the area of the triangle with a height 8 and a base 6. So 8 times 6, 48. So half of that, 24. So we have 24 kips, but where? Third of the distance in from the big end. So a third of 6 feet is 2 feet. So from wherever this line is here, 2 feet in, that's where we'll have 24 kips. So 2 feet in, we'd have 24 kips. And then in the middle, 3 feet, we'd have the 12 kips. So this combination of a uniformly distributed force and a linearly distributed force will show up in the free body diagram as 2 different forces. One from the uniform and one from the linear. And then from that point, once you've nailed down their locations and got the geometry of the problem down, it's the same old problem. Define your coordinate system, sum of forces in the x, y, sum of moments, set equal to 0, and solve. Any questions there? All right, so let's see. So that's those are our examples for distributed forces and the last new content prior to our exam. Next session, Wednesday, we'll probably be spending a little bit of the time on at least one homework problem, and then the rest of it's just going to be exam practice. So it's basically one big practicum session. So come in with your questions to help you out with coming up with questions. Some of you may have noticed if you've gone to the website, I have posted an old exam. In fact, it's not that old. It's the exam I gave last spring. So last spring's exam is posted on the website in the exam directory under old. You should have the exam and the solutions there. So that can be a useful study aid to you if you are trying to determine if you understand things well enough to be comfortable with our upcoming exam. If there are, it would be worth your while to take a look at that exam before Wednesday and come in with questions. So if there are particular questions on that off of that exam that didn't make sense, or maybe you want to explore a little bit more, we can certainly take a look at it. Otherwise, we'll just run a few of the more challenging example problems, and that'll be it for that. Next Monday, we're going to be continuing on a little bit. We'll hit a little bit of material that is off of our second exam or feeding into our second exam. So the content for next Monday will not be part of what we'll be testing on Wednesday, but it will be relevant in that a lot of what we'll do on Monday is basically this same kind of problem as the first step in solving trust problems, which is what we'll be getting into on Monday, is to find the reactions at the supports. So it's the same kind of non-concurrent force system. And so we'll get some ideas about what trusses are and how we approach the solution to a truss problem. And then we'll pick that up again the following Monday. So that'll be our session next time. Anyone have any questions?
I got a quick question.
Go ahead, Doug.
Where did you say that old exam was?
It should be on the website. If you go to the course website, there should be a directory labeled exams.
All right, I'll have to check later because I'm on that key tool.
Yeah, it should be there.
I got handouts, homework, info, lecture, and quiz.
Well, let's see here. Give me 1 second.
Unless I got it updated or something.
It shouldn't be, but let's see here. I will check into it.
Okay.
We're gonna take a little break. Then we'll do our practicum session. But
I found it.
Oh, did you find it? Is there?
Yeah, I had to refresh my.
Okay, I cached it on you. I wasn't sure if I remember. I thought I remembered posting it, but it takes a couple of steps to get it up there, and I might have done the first one and not the second one. But if it's up there, then that's good. So yeah, check that out and see what the exam looks like. The exam is untimed. There's no time limit on it, though I have had students go hours on it. If you know what you're doing, you should be able to be done with it in about an hour. So if you're comfortable with the material, you should expect about an hour. And remember, I will be providing food. I'll be bringing pizza in, probably from La Roma's. It's usually where I end up getting pizza for our 225 classes. So if you have any toppings preferences, those of you who are online now, you get to set the topping preference, I suppose, since you get to communicate with me. But usually I just do plain and a pepperoni is usually sufficient. But if you got something else you'd like, let me know. I'd be glad to accommodate.
Yeah, it works for me.
All right. So we'll go ahead and take a break here. I'm back in about 10 minutes and we'll set up some practicum problems. All right. So we're back from break and I've written up a couple problems here. Let's take a quick look at both of those and I'll give you some time to work on those. A reminder as you're working through the problems, if you get stuck, feel free to ask a question. I'll be pausing the video during the practical time, and then I'll unpause it when I go over how to solve the problem. So in the first one, we've got a simply supported beam with a couple forces on it. That one is basically a review from last week, just keeping those skills fresh. You got to have the basic skills down before adding other things into it. So there you need to find the support reactions, the reaction forces at the support, 2-3 sig figs. And then in the second problem, we've got something that looks a little bit different. It's still simply supported, but now instead of a roller, I'm using a rope. and that's fine. It's still in equilibrium, and you can still draw a free body diagram and do the equations. It all works the same. And one of the things that I like to do when I write up an exam or a homework assignment or something like that is to give you a problem that looks different than what you might have solved before, but that can be solved using the same tools. And if you really get how to use those tools, you'll see after a little bit of thought that it's pretty easy to apply those in a situation that you may not be entirely familiar with. So in this one, we want the answers to 4 sig figs. Any questions on either of the problems? All right, I'll pause the video. Let me know if there are any sticking points along the way. All right, so here are the 2 problems that we've worked on for our practicum session. I have written here in red the answers that I got in my quick attempt to calculate it. Be aware that those answers, when I write those down, sometimes I get them wrong. If I'm going just a little too fast, trying to do everything in my calculator, I make simple mistakes, and I'll get the wrong answer. So if something doesn't look right, don't assume automatically that you're wrong. We'll see it. We'll see how it works out when we work these out. So let's go ahead and start with the first problem, and we'll draw the free body diagram. So here we've got our beam. We've got a pinned support at A, so we will replace that with RAX and RAY. We've got a roller at B, so we'll replace that with RBY. And then we've got our applied forces. We've got three kips pushing to the left. We've got 5 kips up and to the right, and that's shown as 30 degrees off of vertical. And then we've got 10 kips over here. 2 feet, 6 feet, and another 2 feet. So there's our free body diagram. Looks like we got everything: 3 applied forces, 2 supports, everything's in there. All right. So let's get a little more screen real estate here. There we go. All right. So let's define our coordinate system. To the right and up are positive, and counterclockwise moments will be positive. So let's take our sum of forces in the x direction. We've got RAX to the right, so that's positive RAX. We've got a piece of this 5 kip force. And be careful here. This is part of where I've encouraged you to use the angles you're given. I've seen people try to go and figure out what this horizontal angle is, that 60 degrees, and miswrite it as 70 degrees, since we kind of have this natural tendency to try to round or go to 100. I think it has to do with finding change and things like that, trying to go, well, you've got 30 cents, how much to a dollar, etc. But we're talking about angles, not dollars. So get used to just using the angle that's in place. It'll minimize your chance for errors. We're looking for the horizontal component. That would be the opposite side. Opposite goes with sine. So my opposite component here is going to be 5 sine 30. And that's going to go to the right, so it's positive. So plus 5 sine of 30 degrees. Then I've got this minus 3 kips. So a lot going on in the x direction on this one. We'll do our sum of forces in the y direction. We've got a positive RAY. We've got a negative 10 kips. We've got the vertical piece of that 5 kips, and using that 30-degree angle, the vertical piece would be the adjacent side, and adjacent goes with cosine, and that's up, so it's positive, so we have 5 cosine of 30 degrees, and then we have a positive RBY. And then we have our sum of moments about a point, and I'm going to pick point A. That'll knock out RAX and RAY. No moments from those two. It'll also knock out this 3 kip force. Since we're assuming this beam is so thin that it doesn't matter if there's much arm here, it's not going to contribute very much moment. We can estimate it as being just going through the line of action going through the pivot point. So no moment from that one, but we will get a moment from RBY. We will get a moment from a piece of the 5 kip force, just that vertical piece. The horizontal pulls on the hinge, so it's not going to cause a moment. And then we've got that 10 kip force. So we should have 3 terms in our moment equation. The 10 kip force is 2 feet away, so 20 kip feet clockwise, so negative. The 5 kip force, we need the adjacent side. We need that vertical piece. So that's going to be 5 cosine 30, but it is 8 feet away. So we have 8 times 5 cosine 30. That's pulling up. So pinned here, pulling up there, it's going to cause a counterclockwise moment. So that's positive. And then we have RBY 10 feet away. So 10 RBY, also counterclockwise moment. So there we've got our sums, and since we're in equilibrium, those sums must equal 0. So let's go ahead and get these down to some numbers. So for RAX, or for the x direction equation, we've got RAX plus 5 sine 30. Well, 5 sine 30, if you go to your calculator or you happen to know what the sine of 30 is, that's just 5 times 0.5, so that'd be 2.5 minus 3, that's equal to 0. And if we solve that equation, and I'll leave you to do the details of the algebra, we will get that RAX is a positive 0.5 kips. So it's a positive half kip. That it's positive means my assumed direction up here is correct. I assumed it was pushing to the right, and it is. Now you might have looked at it ahead of time and noticed, well, I've got some stuff pushing to the left, but I've also got some stuff to the right. I don't really know which one's going to win there unless you're doing trig in your head. I don't really know which one's going to win. So I had to take a guess, and 50-50 shot. I guessed right. So half a kip. So we've got part of our answer here, and we're going to fill in a table when we're done here for RAX, RAY, and for RBY. Now the specification for the problem was to round our answers to 3 significant figures. And although there was really no rounding going on here, we actually have 0.5 exact here. We'd still formally write it out to meet the specification of the problem to 3 sig figs. And to do that, we'd have to write 0.500 kips. And I'm doing that there because we're not going to use RAX again. So let's go to the y direction equation. If we look at the y direction equation, we find we can't solve it because we're missing too many pieces. So we've got to go to our moment equation. So let's run the numbers down on the moment equation. We've got minus 20. If we go over to the calculator, we have 8 times 5 times the cosine of 30. And since we want 3 good sig figs in the end, we'll round to 5 sig figs. So that comes out to be 8 5 cosine 30 is 34.641 kips feet, rounded to 5 sig figs. And then we've got 10 RBY. And again, details of algebra we can leave to well, we'll leave a little bit of a mystery here, but this is going to come out to be a positive 14.641 plus 10 RBY. So be careful here with your algebra. If you're just used to plugging things in the calculator and ignoring the signs, you could mess up here. This is equal to 0. When we subtract 14.641 on both sides, we get 10 RBY, and that's equal to negative 14.641. When we divide both sides by 10, we'll get RBY is a negative 1.4641 kips. Now that one came out negative. And when an answer comes out negative, it means our assumption was incorrect. We assumed when we drew our free body diagram that the support at B was holding this end up. Well, this this vertical component of this 5 kip force is enough to lift this end of the beam up. The 10 kips down here isn't enough to counteract it. So to keep this in equilibrium, the support at B is going to have to pull down. Now, this would be a design issue. This would be something that we might be working out in design. This is a system that we need to support. Having the assumed direction be wrong here could tell us we can't use the support we wanted to. If we wanted to use a roller here, that roller, if it can only apply a downward force, is not going to be good for this job. So we'd have to find a different support that could apply a downward force to meet the requirements of our loads. So we get a negative 1.641 kips. Now we can feed that back into our y direction equation, where we have RAY minus 10 plus 5 cosine 30, which to 5 sig figs is 4.3301. Now, because our answer came out negative, we have to plug it in negative. We replace the symbol RBY with exactly what it's equal to, positive or negative. Bring the sign along. Don't lose that sign. So negative 1.4641. And that will be equal to 0. And if we run the numbers down on that, we've got a negative 10, we've got 4.3301 positive, and we've got 1.4641 negative. And there we get RAY minus 7.1340 equals 0. So RAY will be positive. RAY is a positive 7.1340 kips. So now that we've got our answers, we can go ahead and round to our final number of sig figs. RAY is 7.13. And it's helpful to factor in or to write in the correct directions. We know RAX was to the right. RAY was up. Since it came out positive, our assumed direction is correct. And then RBY, we had the wrong direction. So we'd still state our answer positive here, 1.46 kips. But the direction is down, opposite what we assumed. So there we go. There are our final answers, rounded to the correct number of sig figs. and specified with direction. So that should match what we had for our answers there. So that was the first problem. Let's go ahead and take a look at the second one. On the second one, we have something a little bit different than what we've done in the past. I supported the left end of the beam with a rope, and the right end is pinned. And hopefully you can all look at that and agree that it's in equilibrium as long as the rope can handle the load, and there aren't any side loads or anything in here. That rope should do just fine. This is in equilibrium. So let's go ahead and do the free body diagram. We've also got this added wrinkle of these distributed forces. So free body diagram will take care of the easy parts first, and then we'll deal with the distributed force. So in our free body diagram, we've got this tension T. Ropes can only be in tension. So if it's drawn this way, it's got to be pulling up. So we've got our unknown tension force T there. Over here, we've got our pin support. And just because the pin support's on the right end versus the left doesn't change it. It's still got two forces, and we'll call those RBX and RBY. And then we've got our applied loads. Here we've got this 400 pound per foot distributed load over 3 feet. The point equivalent magnitude is going to be 400 times 3, so it's 1,200 pounds of force dead in the middle. So at 1.5 feet away from either end of the distributed force. So from the end of the beam, I've got 1.6 feet plus 1.5 feet. So 1.6 plus 1.5, we end up with 3.1 feet. So to get to our first applied load, we have to go 3.1 feet in, and that's where we'll find 1,200 pounds. Now on the other end of the beam, we've got a linearly distributed force. And that linearly distributed force peaks at 500 pounds per foot, spread out over 2.7 feet. So to find the equivalent force, we find the area of this triangle, so 1/2 base times height. So 1/2 times 2.7 times 500. And that gives me 675 pounds of force. Now, where that is 1/3 of the width in from the big end. Well, we've got 2.7 feet of width. Divide that by 3, that's 0.9. So this distance here is 0.9 feet. So 9/10 of a foot. Now, the overall beam width, if we add that up from the original problem, we've got 1.6 plus 3 feet plus another 3 feet plus 2.7 feet. So the whole thing is 10.3 feet wide. So to get from the rope end of the beam to the other force, we just take that 10.3 and subtract off 0.9. So we get 9.4 feet there. We'll need that number for our moment equation. So there's our free body diagram with our distributed forces translated into equivalent point forces. Let's define our coordinate system. So to the right is positive, up is positive, and counterclockwise moments are positive. Well, let's see. So let's do our sum of forces. So sum of forces in the x direction. Well, if we look through this free body diagram, we've only got one force in the x direction, and that's RBX. So we immediately know RBX is 0. There is no reaction in the horizontal direction. So in our table of answers here, we're going to be looking for tension. We're going to be looking for RBX and RBY. And RBX is 0. And when something's 0, it doesn't matter what units it's in, it doesn't matter what direction it's got, it doesn't have a direction defined, it's 0, it's nothing. And I wouldn't worry about writing this out to 4 sig figs as was specified. Don't write it as 0.0000. That's just overkill and not useful because we can't count significant digits that way. Remember, we start counting at our first non-zero digit. If all you've got are zeros, you can't really define how many sig figs you've got. Let's take our sum of forces in the y direction. Here we've got a positive t. We've got minus 1,200 pounds. We've got minus 675, and we've got plus RBY. So that's our y direction equation. And then we have our moments, and I like picking the left side of the beam. You could have just as easily picked the right side and figured out your moments that way. It does not matter what point you pick. I just picked the left side out of habit. So I need my moments about that point, which I'll label as A. That'll knock out T. I'll get no moment from T. RBX we already know is 0, but even if it wasn't, we wouldn't get any moment from it. Everything else we're going to get a moment from. We're going to have a moment from RBY. We're going to have a moment from the 675 pounds of force, and we're going to have a moment from the 1,200 pounds of force. And that's why I needed this number, this 9.4 feet, because I need the arms from my pivot point. If you picked the other end of the beam, then you would need to know the distance to the 1,200 pound force from that end of the beam. So let's go through and find our moments. We've got 1,200 pounds, 3.1 feet away. That's 3720 foot-pounds clockwise, so negative. We've got 675 at 9.4 feet. So that's 6,345 foot-pounds clockwise, so negative. And then we've got RBY 10.3 feet out. So 10.3 feet times RBY. And that would be positive. If we're pinned at A, we push up at B, that'd be a counterclockwise moment. Counterclockwise moments are positive. We're in equilibrium, so we can set our sums equal to 0. And now we've got our equations of equilibrium to solve. We'll go to the moment equation first, since that one usually works out to be the one you can solve immediately. So to simplify it a little bit, we've got 10.3 RBY minus 3750 minus 6345. So we get minus 10,095 equals 0. And if we solve that, RBY will come out to be, oops, did I mess up something here? Let's see, 3,720, 6345. I did 10,065. So if we divide that by 10.3, we get a big long number. Now we need 4 sig figs in our final answer according to the specification for this problem. So we'll keep 6 in our intermediate values. So RBY, I'm going to round this off so I don't have to write all these digits, but I'm going to round it to 6 sig figs. And to 6 sig figs, it's 977.184. And that would be pounds in this case. Came out positive, so we know our direction's good for RBY, which was a pretty good assumption since we only have forces pushing down. It's pretty easy to figure out what directions the other forces have to be going in. But now that we know that, we can go up and substitute that in. 977.184 and solve for our tension. So we've got a negative 1200, we've got a negative 675, and we've got 977.184. And correctly solving this equation should give you a positive answer. And again, rounded to 6 sig figs, 897.816. And that would also be pounds. So that came out positive, so we know our assumed direction's good, and we'd be in trouble if our assumed direction wasn't good here because we're dealing with a rope. And if that rope was pushing down, we'd have a strange situation. Ropes don't generally exert those kinds of forces. Well, we got our final answers, so we can round those off to our final number of sig figs. Our tension is going to be 897.8 pounds, and that's up. RBY, 977.2 pounds, up. So we've got our final answers there. Looking at the problem, we've got a roughly even split between the reactions on the left and the right sides, although this 1,200-pound force is closer to the tension, or closer to the rope. The 675 is much closer to the pin support. So those two effects kind of cancel each other out, and you end up with a roughly even split in load on either end of the beam. And that should match our answers here, 897.8 and 977.2. So we got it right the first time. All right, so those are our problems for this week and for this evening. Wednesday night, we are just working on practice problems. So come in with questions, and we'll be reviewing for exam 1. Have a good night.